Hi everyone, welcome to today's tutorial on advanced chemical kinetics. What is chemical kinetics? What is for sure when a scientist wants to do an experiment? When a chemical engineer or a chemist wants to do an experiment, for instance, he wants to react substance A and B to produce substance B. So he's going to ask himself two questions. The first question you're going to ask yourself is that, is this reaction possible or is the reaction feasible under the specified condition on which he's going to experiment? If the reaction is feasible, you will go on. If it's not feasible, you modify the conditions. The aspect of chemistry that tells us whether a reaction is feasible or not is called chemical thermodynamics. Now, if a reaction can take place, it's feasible or spontaneous, we'll now ask himself, how fast will the reaction take place? How fast will the reaction take place? The aspect of chemistry that explains how fast the reaction take place, the rate of the reaction, is called chemical kinetics. So chemical kinetics is the aspect of chemistry that deals with the rate of chemical reaction as well as the mechanism of chemical reaction. Now, what is rate of chemical reaction? The rate of chemical reaction is defined as the amount of reactants consumed or products formed per unit time. So this is the definition of rate of chemical reaction. The amount of reactants consumed or products formed per unit time. We can still define rate of reaction as the change in concentration of substances per unit time. So we can define rate of reaction as the amount of reactants consumed or products produced for per unit time, or the rate of reaction is defined as the change in concentration of substances, either reactants or products, per unit time. Let's look at this example. A being a reactant going to B being the product. So let us write an expression to present the rate of this reaction. We can write R being the initial rate of reaction equal to d A in square bracket all over dt equal to d B in square bracket all over dt. For this A, we put a minus sign in front. So what do these symbols stand for? This is the change in concentration of A by the change in time. When in chemistry, when a substance is put inside a square bracket, it implies the concentration of that substance. Then this is the change in the concentration of the product over change in time. So we can express the rate of chemical reaction in terms of change in terms of the reactants or in terms of the products. The question is, why do we have a negative sign here? The negative sign there implies that the concentration of the reactant decreases with time. When you start a chemical reaction, as it progresses, the amount of reactants will decrease while the amount of product will increase. So let's assume that you are burning a piece of wood. As you burn the wood is a reactant. It's being turned to ash or charcoal. So as you burn the wood, the amount of wood will deplete or decrease with time, while the amount of charcoal produced will increase with time. So the negative sign shows that the amount of the reactant or the reactant concentration increases and the reaction progresses. Okay? Having understood that, we now take a typical example of a chemical reaction. For example, let's look at the decomposition of nitrogen 5 oxide, which will give us nitrogen 4 oxide and oxygen. It's a balanced equation. How do we relate the rate of chemical reaction of the substances here? So we can write the rate of reaction as the change in concentration of the reactant is nitrogen 5 oxide, or what I call nitrogen pentoxide. Change in concentration, either we use delta or use small letter d, of this N2O5 over change in time. Then equal to, for the product, we say change in concentration of NO2 over change in time equal to change in concentration of oxygen over change in time. This one being the reactant, we need a negative sign in front of it. Then we still look at this reaction involves some stoichiometric number of moles. How do we take care of the number of moles? We divide each expression by the number of moles with minus sign to indicate reactant. This will be 1 over 4, while this is only 1. So this is the connection between the rate of reaction or substances participating in a chemical reaction. Okay? Having done that, we now go into molecularity of reaction. What do we understand by the term molecularity of a chemical reaction? This is the number of particles in a given number of particles in terms of either atoms or molecules in a given reaction. So that is what is meant by molecularity of a reaction. For instance, let's look at this hypothetical example S giving us product P, S plus S giving another product P, S plus Y, P, 2S plus Y, P, 3S giving us P. In this first reaction, we have only one particle, one atom, or we will say one molecule of S participating in the reaction. So any reaction that involves one atom or one molecule of the reactant is said to be unimolecular reaction. In this instance, we have 2 atoms of S or 2 molecules of S, 2 molecules of S. We say this is bimolecular reaction. In this one, we also have 2 molecules, or 1 atom of S and another 1 atom of Y. This is also bimolecular reaction. Then in this one, we have 2 particles of S with 1 of Y, giving you 3. We call it molecular reaction. Also in this one, we have 3. This is also as well molecular reaction. So having understood the concept of molecularity, we now go over to what is known as order of a chemical reaction. So going to order of reaction. The order of reaction is defined as, this is the powers or exponents of the concentration terms in a given rate expression. The powers or the exponents of the concentration terms in a given rate expression. Let's look at this example: A, B, giving us C, giving us D and E. Where capital letter A and B are the reactants, capital letter D and E are the products. The C on top of that represent the catalysts. Small letter A and small letter B are the stoichiometric number of moles, that is numbers used to balance the equation. While small letter D and small letter E are also the number of moles used to balance the equation. I will know in chemistry, rate of reaction is directly proportional to the concentration of the substances. So let's write, with respect to the reactants, we can now say rate varying directly at the concentration of A, that of B, and that of the catalyst. Yeah. So we're going to bring in new terms here. We can call this one M, call this one N, call this one Q. So we now bring in a constant K, A to the power M, B to the power N, and C to the power Q. Now, this is the rate expression for this reaction. Negative sign because we wrote it or it's in terms of reactants. Now, these powers on top is what's called the order of reaction. Letter M is the order with respect to reactant A. Letter small n is the order with respect to reactant B. Letter Q is the order with respect to reactant C. The order of the reaction is different from the stoichiometric number of moles that are not the same. The order of reaction is determined by experiment. So if I want to get the overall order of this reaction, I'm going to add the powers M plus Q. That becomes the overall order of the chemical reaction. So an order of reaction is also different from molecularity of reaction. Okay, having understood that, we now go to different types of reaction order. We have zero order reaction or zero order kinetics. So in zero order reaction, you have this expression A going to B, and then the rate expression to be equal to K, then A concentration A. Arrow varying directly as concentration. Negative sign is expressed in terms of reactant. In zero order reaction, the concentration is raised to power 0. The concentration is raised to power 0. That's why it's called zero order reaction. And in mathematics, when a value is raised to power 0 is equivalent to 1. That means that R becomes equal to K. So in zero order reaction, the rate of reaction and the rate constant are equal to each other. Or we can say the rate of reaction does not depend on the concentration of the substance because A didn't appear here. So if you plot a graph of zero rate of reaction against time for zero order reaction, we have a horizontal graph, meaning the rate is independent of concentration of time. So an example of zero order reaction in chemistry is the decomposition of ammonia on a solid catalyst. Ammonia on a solid catalyst is a zero order reaction. Like on a platinum catalyst. So it's a zero order reaction. So if you look at this, if you want to write the expression for this reaction, the rate is going to write arrow varies as the concentration of ammonia negative, because the reactant I'm using, then I say R equal to minus K, then ammonia be there. Since it's zero order reaction, the power here becomes 0. That means R becomes equal to minus K, or R equal to the rate constant. So you see that the order here is 0, is different from the molecularity, which is 2. So the next type of reaction order is first order reaction. In first order reaction, the rate is directly proportional to the concentration of the substance, rate power 1. This is called first order reaction. The rate is proportional to the concentration of the substance, rate power 1. An example is the decomposition of nitrogen 5 oxide, giving you nitrogen 4 oxide and oxygen. We now have 4 here and we have 2, balancing the equation. So if you want to write the rate expression of the reaction, it's going to be R equal to minus K, then N2O5, rate power 1. Though this reaction is a bimolecular reaction, but the order is 1, being determined by experiment. Then we have second order reaction. In second order reaction, the rate is directly proportional to the concentration of the substance raised to power 2. We will now call this one second order reaction. An example of second order reaction is the decomposition of nitrogen 4 oxide, NO2, giving us NO and oxygen. Yeah. In this case, the rate can be written as R K bracket NO2 then bracket 2. This is a coincidence. In this case, the molecularity and the order are equal to each other. So then we have third order reaction where the rate of reaction varies directly to the concentration of the substance raised to power 3. That is third order reaction. We also have fractional order reactions in chemistry. So having done that, we are going to now look at how we can determine the order of reaction from an experimental data. We will take an example. It says, we have a question on the whiteboard. Derive the rate expression and the value of K for the decomposition of methanol. Have this. So the experimental data given to us, we have 1, 2, 3, we've done 4 times. And then we have the initial concentration of methanol in mole per dn cube, unit of concentration, or mole per liter. The first one is 0.10 mole per dn cube, 0.20, 0.30, and then 0.40. Then we have the initial rate, which is expressed in mole per dn cube per second. So this one is 0.020, and the initial rate for the first experiment. Second one is 0.080. Third one is 0.180. Fourth one is 0.320. So how do we go about solving this problem on the whiteboard? So if you look at the reaction rate will be expressed with is expressed in terms of the rate. So what they gave us is the concentration of the reactor, which is methanol. So we're going to write an expression to present the rate expression for this reaction. So since methanol is what is used, we have because of methanol, we are ignoring methane and carbon 4 oxide. We now write R vary directly at the concentration of methanol, CH3, CH2 to the power, let me call it M. That M is the order of reaction, which we are trying to, that letter M represents the order of reaction. Then you can see write R equal to K, CH3, CHO, M. where R stands for the initial rate of reaction, K is the reaction constant, and then a rate constant here, and then M is the order of reaction. Having done that, we now look at, since the reaction involves only one reactant, that is the molecular reaction, we're now going to use any two set of experiments. I can use 1 and 2, I can still use 3 and 4. If I use 1 and 2, experiment 1 and 2, I will substitute the value of the rate into this. Let me start for the first one. 0.020 for R, then K is unknown, then the concentration is 0.10 raised to power M. I'll call this equation 1. Then I'll do the same thing for the second set of experiment. 0.08, that is the rate, equal to K into 0.20 power M, equation 2. Having done that, what's the next step? We're going to divide equation 1 by equation 2. You two can do the same thing using 3 and 4. You see, you're going to have the same answer. So, we have 0.020 all over 0.080 equal to K. We cancel K, same constant. We now have one bracket, 0.10 all over 0.20 raised to power M. If I divide this, I'll be getting 1 over 4. This side I'll be getting half to the power M. 1 over 4 in indices is 2 raised to power minus 2. Y half is 2 raised to power minus 1, then bracket M. Okay, having done that, we can come down here. We now have 2 raised to power minus 2 equal to, open the bracket, 2 raised to power minus M. They have the same base, that means minus 2 will correspond to minus M. That means M is 2. So that means, what does M stand for? M stands for the order of reaction. So this is the second order reaction. So we are told to find the rate expression. There's no how we can get the rate expression unless we get the order of reaction. Now have the rate equation. So going back to this, we have R equal to K into CH3 CHO to the power 2. That's the rate law for this equation, for this reaction. And we also find the value, we also have to find the value of K, where K is the rate constant. How do we find K? We go back to what we have done, and then we make K the subject of the formula. From here, R becomes, K becomes R all over the concentration of methanol raised to power 2. So K now becomes, we are going to make use of either equation 1 or equation 2. If I use equation 1, my R is 0.020 all over the concentration of methanol there is 0.10 raised to power 2. If I solve this, my K will become 2 as the rate constant. We can derive a unit by unit of rate is unit of the rate of reaction is mole per dN cube per second. While unit of concentration is mole per dN cube. But from here, the concentration is squared, so this should now be times another mole per dN cube. So one of these, we cancel one of these. So we are left with per second, per mole, then dN cube. That means our K will be 2.0 per second per mole, then dN cube. Okay? So we are seeing an example of how to derive or how to obtain the rate law or rate constant and order of numerical data that involves for a unimolecular reaction. Please stay tuned, subscribe to this channel, and we're going to the next tutorial. We're going to look at how can derive the rate constant order for a biomolecular reaction. Thank you.